In the 1980s, I was gifted a most awesome Christmas present. This electronic set was first produced in 1976 for Radio Shack. It was great. You could build 150 different circuits, connecting the components with the wires by bending these springs and inserting the wires. And there was some seriously cool circuits too, like building your own FM radio transmitter. I was probably about 12 years old at the time, and I remember burying a wire trying to connect my house to my friend's house, which was about 3 kilometers away, so we could communicate using this set as an intercom. I never did finish running that wire. It was a lot of work trying to bury a wire for 3 kilometers. At any rate, as much fun as this kit is, it was impractical in some ways and sadly impractical in some educational ways. Am I going to bring this set out with me camping so I can use the FM radio transmitter to communicate with someone else? So now when I teach electronics and robotics, I use a breadboard. Oh, wait, wrong breadboard. I use these nifty little gadgets, which are not a toy, but an actual tool used by professional electronics engineers to design, test, and calibrate electronic circuits. It's a fantastic little invention that allows you to quickly and easily build electronic circuits, making connections using all of these little holes in the board. But how does it work? Let's remove the mystery in this science short. Breadboards are the nifty invention of Robert J. Portugal in 1971. You can insert electronic components and build circuits without soldering anything. You can pull the parts out when you're done and reuse them. You can easily change parts in a circuit and even use microchips. Now, when I first started using them, they were a bit of a mystery to me as to how they worked. I mean, it's just plastic with a bunch of holes in it. So ripping one open is not only highly educational in showing how they work, but also educating you in how to use them. Problem is, ripping them apart destroys them. So I took one for the team and I destroyed one many moons ago for teaching. You've got rows and columns of holes and this strange ditch running down the middle of the board. And you've sometimes got these strips running down the sides, which are removable, like in this case. When we flip it over and peel off the backing, you can see what's going on inside. The holes are divided up into rows in the middle, but split in the center line at that ditch. Then these metal pieces go into the slots in behind these holes. Let's pull one of those out so you can see them. So you can see it's a bunch of metal fingers that make contact with the wires pushed in through the holes. Plastic doesn't conduct electricity, but metal does. And so you can start to see how you can make connections between components by picking and choosing where to insert the wires and components. The metal strips in the middle run widthwise in columns on either side of the ditch, and the strips on the outside run the length of the board. We use these strips as power strips because you typically have to make a lot of connections to power. And look at the size of this board. You can build some pretty big circuits on this board. So let's build up a simple LED circuit. You've got a battery, a current limiting resistor, and an LED. The LED and resistor need to be connected in series, and I'll make use of the power strips. For me personally, I always lock down the breadboard in my mind and make the top outer power strip positive and the bottom outer power strip negative. So I'll connect my battery pack to those connections by simply pushing the wires from the battery pack into one of the holes of the power strips. Now remember, these holes are all connected by the metal strip inside the full length of the board. The moment I plug that wire into any one of these holes, the entire strip is now energized. So I'll now grab a random row in the middle of the board to make my series connection between the resistor and LED. I'll start with the resistor. I'll put one end into the positive power strip, and I'll put the other end into a random row. So now the other side of this resistor is connected to all 5 of these holes in this row and nowhere else. So now I'll put the positive lead of the LED in one of the holes of that row to make a connection to the resistor's lead. And I'll put the negative lead in another row on the other side of the ditch. This way, the 2 leads of the LED aren't connected together, which is a surprisingly common mistake for newcomers. They have a brain fart and forget how the metal strips inside the breadboard connect things together, right? So they'll put the leads of the LED in, the same row. But now the metal strip is connecting all 5 holes together. So the LED isn't even in circuit anymore. It's short-circuited by the metal strips. So I put the negative LED lead over on this side to a random row. It won't reach as far as the negative power strip, so I could pull the battery's negative wire out and put it in that row. But if I was building up a large circuit, I don't want to do that, because now the negative is only connected to 5 holes, 2 of which are already used. So I'll leave it in the power strip that I have designated as negative, and I'll put in a wire. Now, you can use solid telephone wire for this. That's the perfect wire for breadboarding. Or you can get these jumper wire kits of pre-made jumpers, or you can use wires like these, which have what they call DuPont connectors on the ends. In any case, I'm just simply making a connection between the negative power strip and the row of holes connected to the LED's negative lead. Voila, we've completed our circuit and have lit up the LED. Yay. So we can also build up circuits using microchips. As you would see in my online robotics courses or in my in-person workshops, I use the 555 timer microchip all over the place. It is such a versatile little chip. So here's one. I've got it set up as an LED flasher. Basically, microchips are just a package that has a really big electronic circuit inside. These pins each connect to a different part of the internal circuit, and so each pin performs a different job. This varies from microchip to microchip, and you need what they call the data sheet for the microchip you wish to use. In my case, I've got the 555 timer chip memorized just because I use it so often and almost always in the same way. So you put the microchip across the ditch because each of those pins is connected to a different part of the internal circuit. So if you just put it, somewhere like here, remember the metal strips are running this way. So now pin 1 is connected to pin 8. Not only does that completely defeat the purpose, as now I can't even use the microchip because pins that need to be kept separate are now connected, the microchip itself covers the majority of holes and I can't even make any connections. So the purpose of the ditch is to act as an indicator of where the row connections end, and also to allow easy use of a chip removal tool to get microchips back out of the breadboard. In all of my courses, I've moved on to these transparent breadboards. You can see through the plastic now. So you can see the connections inside the breadboard. It removes a little bit of the mystery and also helps in troubleshooting sometimes. For example, at the science camp one year where we built hundreds of circuits every summer for years and years on end, one of the counselors was having problems with their small group of campers as half of the circuits weren't working. So one of the owners, Wayne, and I, we sat there and scratched our heads for quite some time trying to figure out what was going on. Well, it turns out the breadboard manufacturers had made a break in the power strips right here in the middle of the power strips. I'm still seeing this on occasion, and in fact, I ran into this problem at one of my in-person workshops in Sioux Lookout several years ago. The exact same breadboard from the exact same manufacturer, only they changed the design and segmented the power strips in half. So some of the boards were connected full length of the power strips, others weren't. So some people's circuits worked, some didn't. To make matters worse, I did encounter at least one breadboard when I was teaching at the high school here in Eastern Ontario. The power strips were actually broken up into chunks of 5 holes. So in other words, these 5 holes were connected together, and that was it. These 5 were connected to each other. These 5 were connected to each other, etc. All the way down the breadboard. It really makes things unnecessarily complicated to divert from what has become a standard. Oil well. But in the case of my workshop in Sioux Lookout, I figured out what was going on because the boards were transparent. And I could see that the power strips were disconnected in the middle. So we had the battery connected to this end of the power strips, but no power was getting to this end of the power strips. It only went as far as the middle. So if you run into this little problem and you want to use the power strips in the conventional way, just put some jumpers across the break in the middle. Problem solved. All right. Thanks for watching. You know the routine on YouTube. Please like and subscribe and check out some of the other science shorts on this channel and on the Tech Valley Science Center website. Just note the Canadian spelling of center in techvalleysciencecenter.com.